Let's start off this lesson with considering a data set that consists of the weights in grams of human male brains. We can visualize a histogram of the weights. Notice the shape. It is unimodal and symmetric. We discussed these types of bell-shaped distributions in an earlier lesson. Bell-shaped distributions have a special name. They are called normal distributions. So the weights of human male brains seem to follow a normal distribution. Consider what happens when we create more classes. We do this by including the breaks option in our histogram. Let's set breaks to equal to 50. How about setting it equal to 100? Because the population of brain weights is very large, we see that there is a reasonably large number of observations in each rectangle, even for small class intervals. When such small classes have enough observations in them, it becomes possible to stop thinking of the histogram as a collection of rectangles and instead approximate it by a curve. This curve is called a probability density curve. The probability density curve can be used to determine what proportion of the data falls within a given interval. We do this by finding the area under the curve over this interval. For any normal distribution, we need to know the mean and the standard deviation. The mean determines the peak of the distribution, and the standard deviation determines how spread out the distribution is. I'm going to demonstrate this with the online calculator Desmos. Note that when I change the mean, the curve slides left and right. When I change the standard deviation, the distribution becomes more spread out or more narrow. So knowing the mean and standard deviation means that we know exactly what the graph looks like. Now consider the area under the curve between the values of 0.5 and 7.5. If the mean of the distribution is mu equals 0 and the standard deviation is sigma equals 4, then this area is approximately 0.42. Note, however, how the area of this interval is different when the mean and standard deviation vary. So if we want to find the proportion of normal data that falls within a given interval, like 0.5 to 7.5, then we have to know the mean and standard deviation to calculate it. We can see that the weights of human brains is approximately normal. So let's find the mean and standard deviation. We find the mean to be 1,367.704 grams, and the standard deviation is 100.1448. The R command pnorm, with inputs x, mean, and standard deviation, will find the area under the normal curve that is less than the value x. Let's look at an example. Find the proportion of human male brain weights that are less than 1,500 grams. When we run the command pnorm 1,500, elm, s, we find that this proportion is 0.9067577. In other words, about 90.68% of male brain weights are less than 1,500 grams. Suppose that we wanted to find the proportion of weights that are greater than 1,400 grams. Because the entire area under the curve represents all possible weights, we know that it has an area equal to 1. So to find the proportion greater than 1,400, we have 1 minus pnorm 1,400, elm, s, which equals 0.3735383. Suppose that we wanted to find the proportion of weights that are between 1,300 and 1,350. We do this by finding the area to the left of 1,350 and then subtract the area to the left of 1,300. This equals 0.180333, or about 18.03%. Okay, let's step away from this problem for a moment and take a look at user-defined functions in R. A user-defined function is one that performs a specific task that the user programs it to do. The way that it works is that you assign the function a name. Now, we use the function command and any inputs that the function will use. Then, in brackets, you enter whatever commands the function will do. If there is a value that should get outputted by the function, it should be listed in the return command. Let's illustrate this by creating a user-defined function that will calculate the range of a dataset, which is defined as the minimum value subtracted from the maximum value. I will call the function dataRange. The input here will be a dataset, which I'll just call A. Now, in brackets, I'm going to define a variable b that is equal to the maximum of dataset A minus the minimum. I want my function to output this value, so I include the command return b. Once we run this function, it becomes available to use. For example, let's find the range of the human male brain weights. We see that the range is 732. Now, user-defined functions can be pretty complicated. Here is a user-defined function named plotNorm that plots the area under the normal curve corresponding to a given event. Don't worry too much about the programming code here, it's a little complicated, though it may be worthwhile to see if you can figure it out. Let's see how to use this function. It takes 4 inputs. The first and second are the mean and standard deviation. The third input refers to the nature of the area you are trying to find. It can be less than a specified value, greater than a value, between 2 values, or beyond 2 values. For the third input, you enter either less, greater, between, or beyond, and make sure you put those in parentheses. The fourth input is the x value for which the area is to the left or right. It can also be a vector of 2 values for which the area is between or beyond. Earlier, in the male brain weights example, we found that the proportion of brain weights less than 1,500 is about 0.906757. Let's visualize this area with the plotNorm function. So we use the command plotNorm m, s, less, 1,500 to view the area to the left of 1,500. Earlier, we also found that the proportion of brain weights greater than 1,400 is about 0.37353. Let's visualize this area. Recall that we also found that the proportion of weights between 1,300 and 1,350 is about 0.1803383. We can visualize this area similarly, but we use between as the third input and the vector containing the values 1,300 and 1,350 as the fourth input. Okay, let's consider a real-world scenario where we are using normal distributions. Beverage cans are made from a very thin sheet of aluminum, but they must withstand pressures of up to 90 pounds per square inch, which is about 3 times the pressure in an automobile tire. To ensure that can failures are rare, several cans are sampled from each shipment to beverage companies to test their strength. The tests are performed by applying force to a sample of cans until each can is punctured or crushed. Assume that a can is considered defective if it fails at a pressure less than 90 pounds per square inch. Suppose that a shipment of cans is rejected if it's determined that the proportion of defective cans is greater than 0.001, or 1 in 1,000. Now here are the results of a sample of 12 cans. Although none of the 12 cans in the sample were defective, that is not enough by itself to determine whether the proportion of defective cans in the entire shipment is less than 0.001. To make this determination, we should consider the distribution. It is reasonable to assume that the pressures at which the cans fell are normally distributed. Let's estimate the mean and standard deviation of the population of cans of the shipment with the sample mean and sample standard deviation of the 12 that were tested. In R, we can define the variable can to represent the failure pressures of the 12 cans tested. I'll define L to be the mean of these pressures and S to be the standard deviation. Now we want to know whether to reject the shipment or not. The shipment is rejected if the proportion of cans with failure pressure less than 90 is greater than 0.001. Let's find this proportion. We use the command pnorm 90, m, s, which is 0.02848539. Let's take a look at this area. In this scenario, since the proportion of cans with failure pressure less than 90 is approximately 0.028, which is greater than the allowed tolerance of 0.001, the shipment should be rejected. In this module, we explored normal distributions through real-world examples such as brain weights and beverage can pressures. We learned how to use R to analyze and visualize these distributions, and even crafted some custom functions to assist in our analysis. With this knowledge, we're now equipped to handle data that follows a bell-shaped curve, and make informed decisions based on it.